This presentation is on BIM and design for lifecycle safety. We'll start with a brief introduction of myself and then talk about the objectives of this research, introduce the context of this research, and discuss some of the findings from an industry survey that was looking at the tools that were being used for design for safety or prevention through design. Then we'll move on to discuss some of the findings of best practices analysis, and following we'll discuss the potential for BIM for hazard identification, and then conclude this presentation. To briefly introduce myself, I'm currently an assistant professor of architecture at Philadelphia University. Before that, I have been a professor of building construction at Virginia Tech, and I also have had industry experience as an architectural engineer and designer. And my research and teaching interests focus on design technology and management, examining the impact of design technologies and also looking at safety and design. And part of my research has been funded by the U.S. National Institute of Occupational Safety and Health, looking into BIM for prevention through design applications. Within the context of lifecycle safety design, this research is benchmarking the current use of prevention through design tools and also mapping the design process for lifecycle safety design and assessing the need for BIM tools that can support this process. This research is particularly focusing on the intersection of design risk assessment, BIM, and performance-based design. Under the CDM, the UK CDM approved code of practice, the process of design risk management is concerned with health and safety in construction as an integral part of the design process. Design risk assessment is defined as the process of design risk management, which involves identifying hazards or hazardous activities and any associated risks relating to the intended construction work, which includes building structures, maintaining, cleaning, using in certain circumstances, and removing them. Performance-based design requires an integrated approach that has changed the traditional process of design and has the potential to affect building energy use, improve spatial experience, and influence aesthetic decisions. As part of the expanding performance criteria, occupational safety and health is becoming an important component. The notion of performance-based design is closely linked to BIM, which should be able to be used for performance analysis and design renderings, BIM construction models, post-occupancy evaluations, operations and maintenance, and performance verification. The key is interoperability, which allows to collaborate on a design model through construction. The imperative of lifecycle safety has evolved through a number of regulatory changes and initiatives. For example, in the U.S., the National Safety Council's Institute for Safety through Design in 1995 embraced the notion that worker safety can be enhanced through better design and design processes. In 1992, the European Temporary and Mobile Construction Sites Directive resulted in strategic changes to health and safety management throughout Europe, including the UK CDM regulations, which were initiated in 1994. In Australia, the New South Wales government developed the Construction Hazard Assessment Implication Review, CHAIR, a systematic safety and design tool to recognize and abate hazards through construction, maintenance, and demolition. In parallel, the broadening adoption of building information modeling is supporting integrated design, which pursues high-performance standards in user comfort, energy usage, life cycle impact, and design assessment. Design risk assessment. However, there is lack of knowledge on what prevention through design tools designers utilize for safety design and subsequently how BIM can facilitate this process. To better understand this process, this research conducted an industry survey and also a case study research on best practices. The survey was broken up into 5 subsections, including information on demographics, general design protocol procedures in BIM infrastructure, prevention of the design knowledge, standards and regulations, and then the tools and procedures that they used. In this study, 69% of respondents practiced in the United States, while equal numbers of people reported working in the UK and Australia, both at 14%. People from countries outside of these three comprised just 3% of responses. The demographics show that the majority of the respondents were architects at 41%, and then engineers at 26%, followed by construction managers and health and safety professionals. The respondents also indicated that they were mostly executives, principal level personnel at 45%, senior project managers at 28% and 20%, which indicates that the sample was an experienced professional sample. 92% of the respondents believed that considering safety during design can improve occupational safety and health. One of the questions was designed to measure the knowledge of prevention design in the survey sample. The surveys were given the choice of prevention through design, construction hazard prevention through design, design for safety, safety in design, and other similar concepts. And to simplify the analysis of this question, responses were assigned to the category of do not know or know some form of prevention through design. The results in the figure show that general knowledge of prevention design by architects in the US is low, while prevention design knowledge is more prevalent in Australia and in the UK. And within the profession in the US, those that know this concept are mainly engineers, construction managers, and health and safety professionals. The responses by profession show that the participants had experience in hazard identification and risk assessment for construction safety and maintenance and repair, but the engineers and architects from the US had a higher frequency of no experience than other countries. This graph shows the frequency of design tools used in the consideration of construction and maintenance safety issues. In the US, there are no industry standard tools, but the most responses across all professions were material safety data sheets and code compliance checklists. Respondents from the UK picked design guides most frequently for the engineering profession and health and safety professionals. The other professions didn't have enough respondents. And Australia, similar in terms of the sample size, the architects, though being the largest group, showed that code compliance checklists were the most popular choice. Again, focusing on design tools, the survey participants were asked to rate 5 types of design tools from least effective to most effective. Code compliance checklists were rated higher by architects, while engineers and health and safety professionals tended to prefer design guides when designing for safer construction or maintenance. When viewed by country, respondents from the United States tended to rely more on code compliance checklists, while design guides were favored in the UK and Australia. In parallel with the broader industry survey, a number of case studies were conducted to identify characteristics of best practices. It was identified that design guides were preferred to prescriptive checklists because they better supported the creative design process, and prompts about constructability, maintainability, and operability were utilized during the design process. And the focus of designers was on significant risks, which was not necessarily the greatest risk, but those including health and safety risks that were not likely to be obvious to a competent contractor or other designers. And clear and precise visual communication techniques were preferred, including color coding or simplified symbols. And it was identified that it would be helpful to develop design process maps. The following show a few examples of tools that involve visualization techniques, this being a master plan for safety and health in Germany. This is an example of an annotated drawing with color-coded highlights and symbols by Scott Brownrigg Architects that indicates equipment and worker roof access issues. This example is a German visual design guide related to cleaning of glazing systems, and it relates to specific hazards of geometric configurations, access, and support surfaces. And this is an example in Australia at Swinburne University's Advanced Technology Center by H2 Architects, and they designed lighting fixtures for maintenance and operation access considerations and also skylight access. You can see the visual design with the lighting fixtures. Through structured case studies, design process mapping focusing on the use of code compliance checklists, design guides, and visualization tools can help to analyze the gaps in the current processes. Following the findings from the industry survey and from the best practice case studies, specific applications for BIM are being considered. In this example, access issues related to specific systems such as glazing, which check the height for cleaning of this glazing, are being utilized in this BIM application of Celebri. This is another application that checks the two-dimensional distance between skylights and openings. And this is an example that checks particular material properties of glass. So let's conclude this presentation. The review of practices in the US, UK, Australia, and Germany illustrate gaps between best practices and the general application of prevention through design tools. While BIM tools show potential for design risk assessment, there are needs for research of design processes and mapping to guide BIM tool development.